Okay, so our next speaker is Andrea Caratti, coming from University of Torino.
Good afternoon, everyone. I would like to thank the scientific committee for giving me the opportunity to discuss with you about how we faced with a challenge that we got involved in our lab. And the outline of my presentation is here reported. As you know very well, comprehensive two-dimensional gas chromatography is a fundamental technique for the analysis of complex samples, and different are the approaches that can be applied, such as profiling, fingerprinting, and so on. In addition, different detectors can be coupled with this technique, and the most common are the MS and the FID. In fact, the first one combines high specificity through molecular fingerprint and high sensitivity. Instead, the second one is characterized by high stability over time, broad linearity range, the possibility to use predicted response factors, but with the lack of molecular diagnostic features. Chromatographic fingerprinting based on GC times GC patterns give us the possibility to compare analysis for sample discrimination and identification. And by adding the MS dimension, the profiling attitude can be achieved, informing about the chemical composition. The approach, the fingerprinting approach, untargeted and targeted, based on image pattern recognition, provides several steps here reported. And two levels of specificity can be achieved. The first one, based on time coordinates, and the second one, based on the similarity of the fragmentation patterns. In fact, the tracking of a 2D peaks across chromatogram can be done by unique time coordinates, and it is true for both FID and MS. But in the MS channel, the MS spectrum can be compared with the reference spectrum with the NIST algorithm and also with established threshold value to confirm consistent tracking. In the case of parallel detection, such as with MS and FID, image pattern recognition can be applied in both of them, and in the case of the FID, with the lack of the second level of specificity. And generally, the application provides the development of two separated workflows that produce two different data matrices that can be fused together, and the fused data matrix can be used for the chemometrics analysis. Instead, our intent was to fuse the chromatograms from different detectors, generating several fused chromatograms. And from these fused chromatograms, we can extract a unique data matrix that includes FID responses and MS spectrum. By it, high specificity is achieved also in pattern recognition, also for the FID channel. For this reason, we developed, in collaboration with the University of Nebraska and GC Image, a workflow with a script that give us the possibility to convert raw signals, FID and MS signals, with a coherent number of data points per unit time. Then converted images can be fused together and treated as a single one. To note that the FID channel is coded in the virtual fragment M1Z0 and encrypted in the data matrix. Two different applications were used as a test bench. The first one refers to the fingerprinting approach, and the raw hazelnut volatilome was analyzed with the setup here reported. So differential flow modulator, parallel detection with FID and MS with a single quad. Instead, the second application is a profiling of raw fragrances with a thermal modulator, parallel detection with FID, TOF-MS with tandem ionization. That means variable ionization energies. The comparison between single and fused channels results for the first application are shown. In particular, selecting a dataset of 30 samples, we processed separately and with data fusion 30 analytical runs. It means 30 FID images chromatograms, 30 MS images chromatograms, and 30 fused images chromatograms. By these fused processed series, we obtained different numbers of reliable peaks that are those peaks that match in the 50% of the analysis, and in particular 96 for the FID and 20 for the MS. This gap includes FID false positives due to the lack of the second level of specificity, and MS false negatives that derives from the limited efficiency of the algorithm in the pattern recognition in the MS channel that has half of the detectable peaks, 210. Instead, fused channels achieved 30 reliable peaks with a coherent number of detectable peaks, excluding the FID false negatives and compensating the MS false negatives. By the fused data, we obtain good results in comparison with only the MS signal, and in particular good classification for both harvest region and storage time, and also exploiting the FID channel through external calibration curve and predicted response factor, we were able to quantify key markers, and the distribution of some of them important in the classification for storage time are reported here in the slide in the box plot. In the second application, the raw fragrances profiling, the MS channel was used for the quantification by external calibration curve and the predicted response factor. The MS channel at 70 electron volt was used for the identification of compounds with commercial libraries and database. The MS at 12 electron volt was employed thanks to its limited fragmentation for a higher method flexibility and specificity. So, in this application, the data fusion takes place across 3 different channels. And 3 different challenges can address several issues. For example, if collusion occurs, as presented in this contour plot, the FID data stream cannot be employed, but the MS channel can solve the problem by selecting a diagnostic yet characteristic ion. In addition, on the quantification scenario, the limited linearity range of the MS can be solved by the use, compensate by the use of the